So for a time series analysis, so we'll discuss about time series analysis now. So the main idea is to figure out acute effects, to like short term exposures. So what is happening in day to day variations or short time variations. In the earlier example, let's say in a spatial regression or in a cohort study, for example, where we are looking at spatial differences, that's more long term effects. So time series, we are looking at short term changes in exposure and how does that affect the outcome. So the unit of observation here is time. So in this case where we had the individual level data, that's not really time series. But hospital admissions data or number of deaths every day, that's the kind of time series that we are talking about, right? So the unit of observation is time. So your outcome, let's say, is hospital admissions, that varies over time. Exposure, which is, let's say, short term changes in temperature or short term changes in PM 2.5, that is also changing over time. So in the earlier example, when we had hypertension and how does PM 2.5 affect it, hypertension, if it is evaluated at one time point, then that is not varying over time, right? Each individual is measured once. Here, your outcome, exposure and the confounders would vary over time, and that is, so the challenges come from multiple ways, right? Usually exposure and outcome are measured at population. So what do I mean by population level is, let's say it is not individual level data, so it's aggregated data or at some spatial unit. So if we want to study so if we look at our data set, I'll give you this data and the code later on. But this is, for example, daily deaths. So natural causes deaths. Deaths due to natural causes, the daily count. So this is date. So each dot represents one day in Rome. So the number of deaths in one day in Rome. So this is deaths and this is daily PM 2.5 for the same days. So there's a pattern to this. So if you see the deaths, it's going up and coming down. So so this is multiple years worth of data. So there's a pattern to it. PM 2.5 also seems to have some pattern. So again, similar kind of ups and downs. But there are few things to note here is what we want to do. So remember that what is the arrow that we are interested in. Once you fix that, then everything else will follow from there. But that is something we need to fix. So we are looking at short-term changes. This is the arrow that we are interested in. So short-term changes could be 1 day, 2 days, 3 days, whatever. But it is not going to be 1 year. So I'll come to this, but so what are the confounders in this case? So you're looking at short-term changes. I can simplify it further and okay, so the last 2 days PM 2.5 and daily deaths. So what are the confounders in this analysis? So a confounder is what? It will have information about this the last 2 days PM 2.5, and it will also have an information about the daily deaths, right? So that's a confounder. So what do you think are confounders? Recent fire, yeah, so those things can be there. So anything that affects PM 2.5 in short term. So if you think of, let's say, things that do not change over time, are those going to be confounders? Things that do not change over time or things that change very slowly over time. So these are things that happen in the short term, right? So that's our main interest. So the confounders would most likely be things that vary over short periods of time, and the effect goes to the exposure and the outcome. So what they are doing here is, so let's say Y is number of deaths due to CVDs. So why are we using log expectation of Y? So this is because Y's are what? Number of deaths due to CVD on a particular day. So that is a count. So we just showed that we will do a, let's say, a Poisson regression, because we are modeling the log of what? The log of counts. So expected value of, so this is the expected value of Y, the average number of deaths, so the log of that, because we want to do a linear regression. Y's are always positive with number of deaths 0 or more. So that's why the log. So beta naught is an intercept, that's fine. So there are quite a few things here that we need to take care of, right? So our interest is for the pollution, right? So because we are looking at, let's say, 2-day PM 2.5 averages. So that is the main effect estimate of interest. So that is this one. So if that is the main effect of interest, there are certain other things that we need to remove or adjust for in the analysis to get an unbiased or unconfounded estimate of beta 1. So beta 1 is the parameter of interest. So let's go through it one by one. So the first thing is this. So what is this? So this is time trend. So when you look at a time series, so if I go back to the so this pattern, the up-down pattern, is very clearly visible. There is another pattern which is probably not that visible from this plot. And what is that? That is the long-term behavior. So what is the long-term behavior? So are the deaths or PM 2.5, so in this case, what is the behavior of time? Or what is the importance of time? So here you have days, right? So if I collapse this by month, for example, so you will have one dot for a month. Does that make sense? So if I take all the days that belong to one specific month and I summarize it or take the average number of deaths, you will get 1 point. And I can do this for every month from now on. So then this plot would look like one dot for each month. What will that show? Or what does that mean? So if you have annual number of deaths instead of daily number of deaths, and if you plot the annual number of deaths on this plot, what will that show? Like, what does that signify? That is a trend, is a long-term trend. Because what you are doing is, by summarizing within a year or a month, you are removing noise. Right? So this is noisy data, right? Because you have each day. So if I collapse all the days belonging to the first month, then you are removing that noise by summarizing it into one data point. So by removing noise, you are trying to get to the signal. So what is left, and by summarizing in short term, you are removing the short term variations. If I collapse the data for a month, the monthly variation is gone, the daily variation is gone. So what remains is an average over that month. So you are removing this day-to-day variation, and what you are left with is long-term variation. So that is the long-term trend. Does that make sense? So this, if I do that for this plot might look something like this, or it might look something like this, or there might not be any change at all. So that long-term line, that is the long-term trend, which we are not interested in. We want to remove that, because we are interested in the short-term variations. To look at short-term variations, you need to remove the trend. So in a standard, like if you don't have all of these predictors and everything, if you have done a standard time series analysis, you remove the seasonality, then you remove the trend, and then you look at stationarity. It's the same thing, but it's done in a regression setup. So we need to remove the long-term trend. Any questions about that? And how do we remove that is by putting in this so it can be a function of time. It is basically calendar time. So you can put in a function of time. What function will come later? Does this make sense? So this TTI is basically time, calendar time. Any questions? So we are removing by adjusting for time trend. So this you can imagine this to be a linear for now. So a linear term for time. Next is temperature. So because today's temperature might affect tomorrow's PM 2.5, for example. It might also affect tomorrow's deaths. Right? If it gets very cold, you can have more PM 2.5. If it's very cold, you can have deaths due to cardiovascular diseases. You can have more deaths. So that's something that we will need to adjust for. That's definitely a confounder. So see that this is not annual average temperature, this is daily temperatures. Because our exposure is daily PM 2.5 or 2-day PM 2.5. Then it's a short term. Anything that varies in short term gives information about the exposure, gives information about the outcome. Temperature is one of them. Now there could be other confounders. This depends on your data set or your situation. So in this data set, we'll have things like day of the week. So why is day of the week a confounder? So if you are looking at daily deaths and daily PM 2.5 or 2-day PM 2.5, why is day of the week a confounder? Do you think it is a confounder? So if you have weekday and weekends, there might be more or less deaths in the weekday or weekends. Let's say this is in Rome, so you need to know the context as well. So in Rome, the weekends, let's say, are free. So there's less amount of people on the road, people spend more time in their families. So then there will be less traffic, for example. So that would result in less pollution in the weekends. So that is affecting your last 2 days PM 2.5. It could also have more effects on, so let's say they eat a lot on weekends. They might get heart attacks on the next, let's say the Mondays or the Tuesdays. So there is an effect of the day of the week on both sides. So that's why day of the week could be a confounder. Flu epidemics. So if you have If you have data on flu epidemics, so how many people have, whether there's a flu epidemic going on, how does that have information on PM 2.5? I mean, that can have information about the deaths, the daily deaths, that's fine. But do you think it would have an effect on PM 2.5? So this is kind of a proxy variable. So we are not saying that flu epidemics, it is just because flu epidemics are being measured in this data set. But it could be a proxy of something else. This could be a thing about respiratory, so time periods when there are more respiratory distress. That could be indicated by flu epidemics. But there can be doubts about this. So same way in your data set also, you might not be entirely sure that whether I should treat it as a confounder or not. If you have some logic behind it, you should try it with and without the confounder and see whether your main association of interest changes or not. Then we have this, so that's the beta 1 that we are interested in, so that is the main effect of interest. Pollution is our main exposure. So the way it is set up is like a standard regression, right? So standard regression, and this is the Poisson form, so the log of counts. Beta naught is the intercept. F of TTI is a way to model the long-term trends. Temperature is one of the confounders. Why do we have an F of temperature is because temperature, the way it affects deaths is a nonlinear fashion. Because if you have very cold temperatures or very high temperatures, you will have more deaths. In the middle, it's more or less flat. So to model that nonlinearity, we have put it as a F. So we don't know the shape yet. Then there's a beta 1 of the pollution, which is the main effect of interest, and then every other confounder which are daily confounders, short-term things that are varying over short periods of time, that is in the rest of it. So what is not here? So what about the confounders that don't change over time or change very slowly over time? Those are not here, right? Or are they here? It is not mentioned in the list. But how are we are controlling for that? How are we controlling for that? Things that are not changing over time or changing very slowly over time. Exactly. So we are doing it through the time. So by adjusting for this long-term trend in time, we are making an assumption that everything that is not changing over time or varying very slowly over time is taken care of by including that long-term trend for time. Any questions? So if you run this, the standard regression, Poisson regression, and what you are trying to get out of it is that beta 1. So for every, let's say, unit increase or 10 unit increase in the pollution of that exposure, what is the increase or decrease in the average number of deaths? This is the time series regression that we do for environmental health. So if you use this for effect estimation, that's fine. Can you use this for prediction or for forecasting? See, for a forecasting problem, you can do it. So you can train the model on a training set and then you can predict on a test set, or let's say tomorrow. The problem is time is fine because you know tomorrow's time, or let's say a week after's time. You don't know the temperature 7 days in advance. Let's say you have that also. So then we need all of this information 7 days in advance or 15 days in advance. If you have all of that information, then you can use this for forecasting. The problem is you won't have all of this over time. So we use these for estimating the effect of, you use it retrospectively. For a forecasting model, it is better to have fewer number of parameters or fewer number of variables. So if you just had the time and temperature, that would have been a better model for forecasting, because just because you don't have enough data for 7 days later or 15 days later. Or there are other models which we don't use in environmental health, so things like the autoregressive models or the moving average models or the ARMA models. But in those cases, you are dealing with less number of, you are dealing with less number of variables, you are dealing with a few more parameters because of the way the trends are modeled and the seasonality is modeled. But the basic structure remains the same. I don't know if ARMA can use Poisson counts, or do they have that, do they have the link function structure? So I don't know that because I don't use that. But this is the time series that we usually do in environmental health. Any question about this? So just to recap, so the confounding in this specific, like short-term or acute effects, anything that is associated with the outcome but not with, that we have already established. That doesn't matter whether time series analysis or anything else. That is not a confounder because it has to have arrows directing towards the exposure and the outcome. Anything that is displaying long-term variation but not daily. So there is no daily variation in, let's say, length of roads. Your length of road is not changing daily or in short term. Then that's not a confounder in the time series analysis. It might still be a confounder in a long-term analysis. If you are looking at annual average deaths and annual average PM 2.5, then the density of roads would be a confounder. So next is this, so remember that F of the time trend. So how do you model time trends? So we can use a standard linear function, so A plus B times time, that is a function. Or you can have nonlinear functions which are dependent on time only. So that can be modeled flexibly, you don't have any restriction on that. Now if you look here, so temperature has a very specific pattern. So that is seasonality. So over a year what happens? So if it is like this, so if the year ends at this time point, so if it is from here to here, if it is 1 year, then how many times does the line change direction? So if I imagine a line through this, so if the year starts here, going up 1 change, coming down 1 second change, reaches here. So within a year, how many times is it changing direction? So it starts from here, ends here. 1 change, 2 change. So what does this change mean? So the number of times a pattern changes direction. So if you are modeling this, would a linear function be good? Would a linear function be able to capture this pattern? So what would capture the pattern? A linear function doesn't change direction. What is the next after a linear, what comes after a linear? Quadratic, or what is it, the shape like? It's a parabola, right? So it is something like this or the other way. How many times does this change direction? Once, right? So it is here. So the next would be a third degree, goes up, comes. This is a third degree polynomial, right? So linear, quadratic, cubic. So changes direction twice, that means maybe a cubic polynomial is a good option. So the degrees of freedom is a concept which is related to this. How flexible is your function? When is a function more flexible? When it can change direction more times. And what happens with that? So the degrees of freedom are increasing. How free is it to move around? So a linear function doesn't change direction. A quadratic function changes once. Cubic changes twice. A fourth degree polynomial changes thrice. So that's why you can model it flexibly. So if and why would I use, so the number of degrees of freedom would now be what? So if you have multiple years of data, every year it is changing direction twice. So let's say you have 6 years worth of data. How many times does the line change direction? 6 years worth of data, every year it is changing twice. So 12 changes. So that would be the degrees of freedom you would use to model the trend. So if it is 6 years worth of data, this is the first year, 2 changes, and it will go on like this. So to model time flexibly, that's what we see. So if you have, so you could have more changes also, right? So this is not very clear, but there's something going on up here, there's another jump, and then it's coming down. So in this case, if I want to model it more flexibly, 1 change, 2 changes, 3, 4. So now you have a 4 changes. So 4, if I have 6 years, 6 times 4, 24 degrees of freedom. So this is based on your assumptions. This is something that you will need to specify in your, when you are writing the code, you will have to either specify. There are other ways to do it using, you let the data choose it. That's also possible. So that's something called a penalized approach. Any questions about this? Yeah, so that's basically cubic spline is that, right? So if you can use more than one. So there's something called the basis functions. So maybe one function is not good enough to estimate your changes. So what do I do? So I'll just briefly explain that. And there can be weird functions, right? Weird trends. So if I have to do this, then I need something called a basis, a B-spline. So B-splines are things like this. So imagine that, so this is the function that we are trying to approximate. And imagine there are families of functions. These are the 2 extreme members of the family. Then there are small functions in between. So there are these ranges where there are certain functions. So there are these family of functions. I can use this family of functions by weighing them. So you can do a weighted average. So simple weighted average. So at this, I will give, let's say, more weight to this. So it's a combination of this, any function that is there at this time, at this x. So I can use, so these are just different functions, so f1x, f2x. So I can do a wi fi of x, and then sum over I equals, if there are k basis functions, this can approximate this weird function. So that is called a B-spline. So that increases the number of parameters, but you can use a penalized approach to get at this. But the main idea is one function can be approximated by a family of functions. You don't need to go into the mathematical details of this right now, but this can be done. So there are a lot of ways to flexibly model time trends. So it's the same thing. I mean, if you use a very flexible function, the problem comes with number of parameters are increasing. Because in a linear function, you have 2 parameters. In a quadratic function, you have 3 parameters. So if you keep increasing the degrees of freedom, your number of parameters is also increasing. So then the issue of estimating it correctly comes. So if you are letting it be very, very flexible, then it will be a very wiggly curve. And that may be overfitting. So in this case, this is a very smooth curve. This is a less smooth curve. But this you will see that there is a lot of change. So it is trying to figure out variations in very, very short periods of time. So any change it will try to move. There are problems with doing that. If you don't have enough data, then this might be overfitting. So the same data, I mean, you can use those different degrees of freedom depending on your assumption. So let's say if you use 4 degrees of freedom, so this is the final one that they are using, the 4 degrees of freedom per year, because there is a small bump here. That one is 2 degrees of freedom per year. So the one that I showed you, 2 changes. This is 6 degrees of freedom. So this is becoming too wiggly. So the choice of the degrees of freedom, you can either do it by doing some model selection based on the AIC or any other criteria. The other way to do it, you let the data decide using a B-spline approach. And then it will tell you what is the estimated degrees of freedom per year. So I think let's go ahead and show you the analysis, then I'll come to lags. So I'll give you the code later. Right now, let's just focus on going through it so that you know what is happening in the code. So this is what the data looks like. So you have the city, which is the same in this case. You have date, which is 2006 1st January, so the first day of January in 2006. And so this is the time series data. So the unit of observation is time. Spatial unit remains same, so there is only Rome. Then you have month and day, and day of the year, day of the week. So day of the week goes from 0 to 6. Day of the year would go from 1 to 366. So NAT is the the deaths due to natural causes. CVD is deaths due to CVD. Respiratory is due to respiratory causes. T mean is the average temperature on that day in Rome. So the same day when the deaths are being reported. So deaths are, I mean, you are counting the total number of deaths in a day and this is the 24-hour average of that day. Similarly for PM 2.5. So this is the data set. Right now I'll not share. I mean, you can take I'll share everything at the end. So you can take a look at this. So if I plot the number of deaths, let's see what happens. Okay. So we have seen this earlier. So this is deaths due to natural causes, and there's clearly some seasonality and some maybe upward trend in the long-term trend. Okay, so how do we figure out? Let's see. So what I'm doing here is, so we know the number of years in the data set. That's what we are trying to figure out. So length of unique, so y is the year variable. So the number of unique observations of that is the number of years represented in the data. So number of years is 10. So that's 10 years worth of data. Then we are ordering the data set. So because in a time series you need to have things in order. So the first day, the second day and so on. So that is, so the data and then within brackets this thing. So this is ordering by date. And then I'm creating a variable which is called trend. And trend is what? It is just a numeric variable going from 1 to whatever number of days there are. So if I go back to the data, so there's this variable. So I've just created a simple numeric variable. So now I'll fit this model. So the model is, so our final objective is to do it with PM 2.5. Right now we are just fitting the trend. So there's no exposure. So this is just modeling the number of natural deaths with a time trend. I'm using 2 degrees of freedom per year. The data is given, and this NS is a natural spline. So natural spline means that I am telling you fit a usual spline with 2 degrees of freedom. And GLM, I don't know how many of you know what GLM is. So GLM is generalized linear model, because this is it's not it's a count data, so number of deaths due to natural causes. So that's why it's a generalized linear model. So the generalized linear model is because the linear regression, since we are changing the type of y, so the logistics or the Poissons, they are called generalized linear models. So if you change anything on the left hand side of that equation, that's called generalized linear models. If you change something in the f, that's the generalized additive models, to model flexibly the relationship of x and y. But this is a generalized linear model. So where are we saying that is here? So family. So what type of data is it? So this one says quasi-Poisson. So how many of you know what is a quasi-Poisson? Anyone knows what is a quasi-Poisson? So usually if you just do it with this, so if you remove the quasi, let's copy this whole thing. I have to include the produce lines. Okay, so where is the model output? Summary. Okay. This is what the output looks like. So it tells you what formula you have used, and then it gives you this whole list of parameters. So there are so many parameters that you are using, because remember we have used 2 degrees of freedom for every year. So that is 20. So these are all mentioned here. So see 20. So 20 parameters and the intercept. Now why Poisson and why quasi-Poisson? So usually you would not go straight to the model, right? So what you would do is you will summarize your data. So let's say if I do the mean of the average number of deaths in this data set is 72. So the average number of deaths is 72. The variance of the number of deaths is 133. Yes. So if you assume a Poisson distribution, so if you assume your outcome to be distributed as a Poisson, that makes an assumption that your mean and variance are the same, because Poisson distribution is designed in such a way that your mean and variance would be same. Here it is not the same. It is more than what it should be. So it should be somewhere close to 72. It's 134. So that's why we have to use a quasi-Poisson distribution. So the quasi-Poisson, what it does is it assumes that there is an extra variance attached to the Poisson distribution. It will not change your effect estimates, it will change your confidence intervals. So when I ran it using a Poisson distribution assumption, which is family equals Poisson, you'll see that this line here, the dispersion parameter for the Poisson family is taken to be 1, which means there is no over dispersion. It is assuming that there is no over dispersion, and it is doing the estimation. But that's not what the data says, so we'll use quasi-Poisson. Yeah. With the data, so you check. So I check my variance and mean of that variable in the data set. But now what will I do with it? So I am trying to fit a Poisson, but my data says that mean and variance are not the same. So that's why I'll go with quasi-Poisson. So the same thing can happen with binomial also. The binomial, you know that your variance function should look like, mean and variance has a relationship. So for all generalized linear models, that's the problem, right? The mean and variance are related, not in a normal distribution. So if you know that if you know the mean of let's say a binomial distribution is P, the variance should be P times 1 minus P, right? So if you see that your data doesn't follow that, then you would go with quasi-binomial, or in this case quasi-Poisson. So it has to be checked before you do the model. So the first thing that you will notice here is that, look at this, the dispersion parameter for the family is taken to be that 1.39. So it is assuming that it is, so now it is making or correctly estimating that the variance in your data is more than what it should be if it was just a Poisson distribution. So it is not, so that's why it is more than 1. So it is over dispersion. There can be under dispersion as well. So when you have less variance than expected, this one is estimating that. So there is an additional parameter that is being estimated. But otherwise it looks the same. Oh, sorry. So this is that plot. So you're fitting a time trend with 2 degrees of freedom per year for 10 years. So the same thing can be done for 4 years and 6 years, and finally you have to make a decision that whether you want 4 years or 4 degrees of freedom per year or 6 degrees of freedom per year. So this and okay. Okay, so this is where we are putting in the exposure now. So we are trying to figure out the effect of short-term changes. So in this case, short-term change is what? So the PM 2.5 right now is that same day as PM 2.5. As if you remember the data set, it was by day, right? So 2006 1st January was the first day. It had a number of deaths and the average PM 2.5 and average temperature on that same day. So that is what is being used here as exposure. So model 1, so this is the natural number of deaths, PM 2.5, we are using the same trend but with 4 degrees of freedom per year, and we are using the quasi-Poisson. So nothing has changed other than adding in a PM 2.5. Same regression, same family. So this is a data with, a model with no temperature, because we are not adjusting for temperature or any other confounders. So what does it look like? Okay. Oh, sorry. So it is giving you an output, so we have just formatted that output. So this is the beta. So the beta is for 1 unit increase in PM 2.5. Right, so that same equation. So if we have natural number of deaths, average number of deaths, and the PM 2.5 right now it is just daily average PM 2.5, but 1 unit increase. So that change in the average number of deaths in the log scale, that's 0.0014, because you are modeling the what? You are modeling log of expected value of y, which is the log of average number of deaths. So that's the beta. To get back to the original scale, you need to do what? You need to exponentiate, right? But before doing the exponentiation, you need to look at meaningful changes in PM 2.5. 1 unit change in PM 2.5 in a space like Rome is not that interesting. So we'll first multiply your coefficient by 10. So this is for 10 units change. So 1 unit change in PM 2.5 is, so if I do log of E of y at some this minus so this difference is what? So if PM 2.5 is x versus PM 2.5 is x minus 1, then you get some average number of deaths at PM equals x and some average number of deaths at x minus 1. Now if I subtract them, what do I get? So the beta naught gets cancelled. Beta 1 times x and beta 1 times x minus 1. So what is left if I subtract? It's just beta 1, right? So this is, so log of a minus log of b is this. So how do we simplify that? So this is log of right. So this is, so if I exponentiate this, then the ratio at x and x minus 1, that's, so this will be e to the power beta 1. So that's the incidence rate. Any questions about this? So you just plug in the values of x and x minus 1, that's, and take the difference. So that's 1 unit change. So if I was doing a 10 units change, I have to make the change here, not at this level. So PM 2.5 would be x and this would be x minus 10. So then this would be 10 times beta 1. And then you have to exponentiate accordingly. So that's what is happening there. So that's why for 10 units change, what is the change in the ratio? So that's 1.47. And this is the confidence interval for that e to the power 10 beta. So now if we put in temperature, so PM 2.5 remains the same, the NS, the natural splines for time trend remains the same. We are adding a temperature average. So average temperature on that day. So it doesn't change much. I mean, the effect estimate, you will see that this is 0.001 and this is also the change is very small, right? So in the IR10 also, but it shows up in the IR10. So if you change it by 10 units, then the ratios are 1.4 and 1.2, right? So now in that equation in the slides, you remember that we had fit a flexible function for temperature as well. So that can also be done. So again, choosing the degrees of freedom, that's again similar method, but we'll go ahead and do this. So now you see that what has happened here. So these are the three things together. So what is happening here? So the first one was just a time trend, right? No temperature, no nothing. So the IR10 was 1.47. Next, if you put in the temperature as a confounder, it's 1.21. Now if you put a flexible function of temperature, it is reversing direction. So what does this 0.87 mean? So with increasing PM 2.5 the number of deaths are decreasing, which is slightly counterintuitive, right? That's not what we expected. So why do you think that is happening? So the stat will not tell you, the R will not tell you. You need to tell. Why do you think that is happening? Let's think of some reasons. So temperature is a confounder, so we have taken care of it. I mean, either by linear or by flexibly modeling temperature. So there are issues in how we have set up our exposure. So what is the exposure that we are using now? The exposure is PM 2.5, but when? So remember yesterday when we told you, how are you measuring, when are you measuring, how long are you measuring? So what is that? Right now, the number of deaths is for that day, and the PM 2.5 is also for that day, the same day. So if you think of the biological or the physiological systems, people are dying today. So it is very unlikely that the exposure that is happening today is going to affect them. So what happened yesterday is probably more important, or what happened day before yesterday is probably more important. So we are not using the correct exposure. So that you will anyway do correctly, because when you are setting up your question, you will say that whether the last 2 days exposure is affecting today's deaths. Right? So that was the whole starting point. But if you start doing the analysis right away, this is what you will encounter. Okay, so now comes the lag part. So I'll hope you, yeah. So now how do we make lags, or what is the lag? So this is for temperature. So what we'll do is, I'll go ahead and create these things. So now comes the lag. So why is lag important? I think we have already established that. Now what lags are important? So is it yesterday's temperature, or is it day before yesterday's temperature, or the last week's average temperature? What is important? So how will we find that out? So first thing is we need to create the lags. So creating lags is fairly simple. So if I go back to the data and show you what it looks like. So that 21.9 on the top for PM 2.5, that is the PM 2.5 on which day? 2006 1st January. What about this row 8? 2006 8th January. What is the PM 2.5? It is 42.49. So if I stand on 8th of January, if I ask you what was the PM 2.5 level yesterday, what would be the value? So this is the day we are standing at. So this here, so this is today. So what was the PM 2.5 level yesterday? 41.66. What was the PM 2.5 2 days ago? It was 41.54. So a lag is a variable which is just like the original variable, just shifted down. So if I take this whole column and shift it down here, shift it to the right and one step down, then this number will come here. Any question about that? Right? So you are taking this column and pushing it down. So then this 42.49, and there will be another variable with values 41.66. That is the lag, like a 1 day lag. If I bring this and push it 2 steps down, then the 41 will come here. That is a 2 day lag. So in R we can create these lags by shifting the variable and pushing it down. So there are, we have the function is there it's called lag, and then you need to specify what lag, like how many days. But the basic is very simple. So you push it to the right and bump it down by however many lags you want to create. Right? So once you have that, you will have, so what new variables will you have? You will have a PM2.5, you will have a PM2.5 lag 1, lag 2, lag 3 and so on. Just simple variables, it's another set of variables. You are creating the variables. If I want the last 2 days average, how will I do it? So I'll have a lag 1 and a lag 2, same way, and I take the average of those two variables. That's simple, like last 2 days moving average. So this is what I am doing here. So I am creating lag. So lag, the variable is PM2.5, lag at what duration? 1. This is the second, third. So here 1, 2, 3 means how many steps you are coming down. So lag 1 means yesterday's temperature, lag 2 is day before yesterday's temperature, and so on. So let's go back to the data and see. So this is what it looks like. So that 21.9, in the first lag it has come down 1 step, then the second, third, fourth, and it is going down. So this introduces the issue of missingness, because obviously you don't have any information before 2006 1st January. So those, if you are using these lags in your model, those rows would be deleted because they don't have any information for the lags. But is that, so this 0, 1 means this is the average of today's exposure and yesterday's exposure. L2 and 5 or 2 to 5, that means it is the average of the last, like 2, 3, 4, 5. Right? So that is, it's simple averages. So that's how we create the lags. So once you have these variables, they are just like any other variables, right? So now if you want to do a lagged analysis, so let's say I want to look at yesterday's temperature and today's deaths. Instead of using PM2.5, I'll use PM2.5 lag 1. That is the lagged exposure or lagged analysis. If I want to look at day before yesterday, same thing. Just use the correct variable, that's it. So I'll see if I have this. So when you go through the code sequentially, you will see where this is. So we have come up with a sort of a sub-final model which looks like this. So it has some. So instead of using just the average temperatures, we are using the lags of temperature, because remember when we said that the last 2 days PM 2.5, the last 2 days the time varying confounders which are varying in very short amount of time, which is one of the examples is the temperature. So the average temperature today and yesterday, I am using that as a confounder. So L01 is lag 0, lag 1, average of that. And this is something that we have done. This is the number of degrees of freedom is something that we have calculated earlier. So when you go through the code, you will see where it is calculated. So this is temperature variations in the last 2 days or till yesterday. This is 1 to 6. So if I go from yesterday back 1 week, so it's a 1, 2, 3, 4, 5, 6. So 6 days average. So, and this is done for hot temperatures and cold temperatures. So why is that? Because remember when we said that the relationship of temperature and deaths is going to be non-linear, right? So in very high temperatures or very low temperatures. So that's what this is trying to do. So it is fitting 2 splines to capture that. One in the hot period, one in the cold period. This is the same long-term time trend with 4 degrees of freedom per year. And this is the day of the week. So we are treating it as a factor. Factor means it's not a continuous variable. So the 1 and the 6, the values don't mean anything. It's a factor. So whether it's Monday or Sunday or whatever. So that's the day of the week. Family is still quasi-Poisson and data remains the same. So this is the model that we will start with. So this has no PM 2.5, right? So this is just without the exposure. So we have brought in all our confounders and all our time trends, everything is now in this model. Now we will put in the appropriate exposure. Right? So this is what it looks like without the exposure. So what is happening here is we will keep that base model and add things or modify the exposure. So the first model is you are updating model 5, which is that model without the exposure. So what will we use as exposure? The first model is today's exposure. So today's PM 2.5 average. Next model, instead of using today's, I am using yesterday's, then day before yesterday's, or this is one at a time. So one lag at a time. So instead of using today's PM 2.5 average, I am either using yesterday's or day before yesterday's or the day before that and so on, right? So each of these models are doing that. Any questions about this? So that's why they are called single lag models. So single lag means you're just taking one lag at a time. Yeah. Yeah, I'll come to that. So let's finish this. So which lag is most important, we'll see that. So here are the results, right? So lag 0 means today's exposure. So what is the IR10 for that? So 0.48. So if we, it's difficult to see this. So the first one is lag the same days, then it's lag 1, so yesterday's, then 0.92 is the one for 2 days before. So what is happening here? So what is the meaning of these coefficients? So can you see a pattern in this? So we can do it here also, it's the same thing. So that top one, that's today's. Yesterday's exposure, it's increasing. Then it drops and keeps dropping. So what was the lowest one? Lag 5. 0, 1, 2, 3, 4, 5. So now if you, yeah. The IR10 is the exponential of that. The beta coefficient is here, it's the same way. Yeah, so this, oh, okay. Sorry, this has mixed up. So this, ignore the labels have changed. So we'll focus on the coefficients. So we can look at this beta anyway. So this is increasing at lag 1, it keeps increasing in lag 2, and then it keeps dropping. So if I plot this thing on a simple scatter plot, so what will it show, or what will it look like? So it will show a high effect at lag 1 and 2, and then it keeps dropping. So what is the meaning of that? The effect of PM 2.5 is happening at a lag of 1 or 2 days. So the strongest effect is showing up either yesterday or the day before yesterday. This is after removing everything that was long term and all of that. So that's how you do a single day lag analysis. Simple regression is just you are changing the variable. If you want to look at cumulative averages, so let's say what is happening over 1 and 2 days. Instead of using the single lag, you will use the average of lag 1 and lag 2 and same model. So that will give you cumulative averages or cumulative effect. Okay, so let's take a look at this. So this is the same. This is lag 0 and 1 together. So today's and yesterday's. 2, 5 is 2, 3, 4, 5, and 0 to 5 is this 0.0011. Now what can happen in a lot of studies is, or a lot of these kind of lag analysis is, depending on how the exposure is affecting your outcome, you will see a delayed effect or a consistent effect or a very, very acute effect. So if I plot those effect estimates here, so it is lag 0, this is lag 1. So the lag 0 in this case, even if whatever is the effect estimate, it doesn't really make sense because your exposure has to happen before your outcome. So we'll ignore this for a moment. So L1 means it is somewhere here, let's say, and this is the coefficient, right? So beta. So L2 might be here, then L3 might come here, and L4 and L5. So what this shows is the effect is happening at lag 2. The strongest effects are more recent to the outcome. This can also be, so instead of this, the thing can come down slowly. That means there is a sustained effect. So let's say things like heat, which can occur over a longer period of time. In those cases, maybe the last 1 week's exposure is going to have a strong effect. So if you see things like this, there can be things which take more time. So let's say if you are looking at outbreaks, so then you might not find anything. So you might find a peak later, and then it might drop suddenly. So then that is what you are trying to figure out. The same thing can be done for, let's say, people who are doing maternal and child health or pregnancy outcomes. The lags in that case would be trimesters, let's say, or the month. But the effect the analysis would be the same. So then you can break it down by 3 months. So there will be one for the first trimester, one for the second trimester. So if things that happen very, very early, your third trimester result might be, you might not find much. Second trimester might not be much, but the first trimester effect might be high. Or if things that, it can be any direction, right? So it can be like this, it can be like this. But it's the same lag analysis. Any questions? Can you use the same, can you use multiple lags in the same model? Yeah. Yeah, so I think the labels got messed up a little bit. RR, yes. So so it has got messed up in the code. So yeah. So this is, the headings got shifted in. That's the main issue. So, yeah. Yeah, so it was defined like that for, let's say, this specific problem, we have defined it. So what would happen is you can model it flexibly. Instead of having two different splines, you can put in one with so it is basically a U-shaped curve. So we had done it split. So we had done one for this side, one for that side. The middle it's not changing much. But you can do it using one. So this is just for demonstration purposes that we had done this. But the question now is, can you use multiple lags in the same model? So I have created my lags, right? Lag 1, 2, 3, 4, 5. Can I use all of them in the same model? Yeah, so it is very clearly correlated, right? So yesterday's temperature is a good predictor of today's temperature. So using them together is going to be a problem if you just use it in a standard regression setup. So that's where the distributed lag models come in. So that is the distributed lag models or distributed lag nonlinear models. To account for this collinearity or the relationship, or you look at, because what you are ultimately trying to do is looking at a cumulative effect kind of thing. So what is happening over the last week? And what is happening across pregnancy? So if I look at it together, then to take care of this collinearity, there are methods like the distributed lag models, which are penalized models, to account for this correlation between lags. So I think we'll go through that. There's one more section in the agenda, which is the mixtures. I don't know how much you are up for that. So that will be a much more complicated one. That's up to you. We have kept some space for DLLM maybe after lunch. Do you want to do DNLM now, or do you want to do mixtures now? Or do you want to try out the code? Try the code, so I'll send you the code then. So so these things here. So TS model of splines, data.table. So mainly splines and data.table and dplyr. Dplyr I think you already have. So you can go ahead and install them. These things you can ignore for now. So the source code. Remember to change your working directory. So we are sending the code, but you can go ahead and start installing packages because they will take at least, let's say, 5-10 minutes. TS model, splines, DLNM, and data.table. LM test is not required right now, so you can, I mean, if you can install it. Familiar with it? It's just it's with an extension of .rds, and the command for reading that is read rds. So it's specifically an R data set. It takes less amount of space. So I would recommend you start with looking at the data, just make sure that you can summarize the data, and then run a few of those GLM models and then creating the lags. Once you create the lags, the rest of it is more or less similar. I mean, you're just making your own regression models with these specific variables. At least up to making the lags, that much you should be familiar with. Which one? I am not sure. I mean, it has, right? Okay, let's do it a little bit. So everyone has got the code and data set. Yeah, it was his only. So in the original data set, you will not have these variables, these things like n years and trend there. So you have to run it sequentially for it to work, because it will. So this trend variable, for example, will be used later on. So don't skip those.